Okay, so here's part 2 of the electrodynamics practice final exam. So back with number 10. A long solenoid of radius r carries n turns per unit length and current I. Part A, find the magnetic field inside and outside the solenoid. So this is a magnetic vector potential of a solenoid. So for a long ideal solenoid, we have that B equals U naught N times I, inside and 0 outside. So just for part A, find the magnetic field inside and outside the solenoid. That would be this piecewise function for our magnetic field that's equal to this top U naught N times I times Z hat for R, lowercase r is less than capital R, and for the lower portion of the piecewise function, 0 for R is greater than capital R. Part B, find a suitable vector potential A for both regions. So here for part B, vector potential, use cylindrical symmetry and choose A equals A sub phi of R phi hat. And for cylindrical coordinates, we're going to get B sub z equals 1 over r d dr r A sub phi. So inside here, first, we'll do the inside. That's going to be 1 over r ddr of r A sub phi equals U naught Ni, and ddr of r A sub phi equals U naught times N times I times R. So r A sub phi, that equals U naught N I R squared over 2. So we're going to wind up with A sub phi equals U naught N I over 2 times R, lowercase r is greater than capital R. Right here outside, our B equals 0. So we have 1 over r d dr of r A sub phi equals 0. R A sub phi is going to equal to C. So A sub phi equals C over R. Now continuity at lowercase r equals capital R. That's going to give C over capital R equals U naught N I over 2 times R. And C equals U naught N I R squared over 2 when we isolate C. So we could go up here and we could say, therefore, A sub phi equals U naught N I capital R squared over 2 lowercase r, where lowercase r is greater than r. And we'll have this piecewise function, our A, our vector potential A here, would be this piecewise function, U naught N I over 2 times r phi hat, where lowercase r is less than capital R, and U naught N I R squared over 2r v hat, where lowercase r is greater than r. Okay, so let's see here. Part C, we want to explain why A can be non-zero even when the magnetic field B is 0. So the magnetic field is B equals a del operator crossed with A. And we could say here a vector potential can be non-zero even if its curl is 0 in a region. Outside the solenoid, B equals 0, but A does not equal 0 because the vector potential still encodes the magnetic flux confined inside the solenoid. Okay, so that's letter C, A, B, C, and that's good for number 10. Moving along. Number 11, uniform magnetic field. So right here, a uniform magnetic field points in the positive z direction, z hat direction, and changes with time as B of t equals B naught e to the negative t over tau. The field fills a circular region of radius capital R. Find the induced electrical field E sub phi of RT. Okay. So A and B. for R is less than capital R for A. Okay, so this is Faraday's law, an induced electric field. So we're given this function, okay, and we're given the magnetic field. The magnetic field fills a circular region of radius R. Okay, that's more textbook stuff. By symmetry, that electric field is E sub phi times that R of t phi hat. Faraday's law, here it is. Textbook, notebook stuff. Very famous law inside. Now we have R, lowercase r is less than R. Okay, so we're dealing with the flux through radius R. Okay, and that's going to be equal to B of t times pi R squared. And so that E sub phi 2 pi R, that's going to be negative 2 pi R squared. And then the derivative, that magnetic field with respect to time dB dt. So E sub phi equals negative R over 2 dB dt. And then getting dB dt by itself, that's negative B naught over tau equals E to the negative t over tau. So we wind up getting here for part A, E sub phi R of t equals R B naught over 2 tau times E to the negative t over tau. And lowercase r, that's where lowercase r is less than capital R. Okay, so that takes care of inside. And now we do outside, where lowercase r is greater than r. Okay, so here, what we could say is the flux only comes from the circular magnetic field region here. So E of sub phi, of 2 pi r, that's going to be negative pi r squared dB dt. And that's going to become negative R squared, negative capital R squared over 2 lowercase r dB dt. So what we could say here is E sub phi of R of t equals capital R squared B naught over 2R tau times E to the negative t over tau, where lowercase r is greater than capital R. So here we could say the direction is determined by Lenz's law. Since B is decreasing in positive z hat, the induced electric field circulates counterclockwise as viewed from positive z hat. Okay, so that takes care of number 11. Moving along to number 12. Okay, so number 12. We have a parallel plate capacitor, has circular plates of radius r. The electric field between the plates is approximately uniform and given by E of t equals E naught sine of the Wt. Find the displacement current density. Okay, so let's see here. That's omega. I shouldn't call it W, it's omega. Okay, angular frequency, omega. Sometimes I call it W by accident. So part A, find the displacement current density. So the displacement current density, we're given this function from above. So that's going to be, the displacement current density is J sub D equals E epsilon naught, and then derivative of your electric field with respect to T. So J sub D equals E naught omega E sub naught cosine of omega T Z hat. So that would be your displacement current density right here, that J sub D. Part B, find the magnetic field between the plates as a function of the radius, lowercase r is greater than capital R. So magnetic field between two plates. We're going to use the Maxwell-Ampere law. Here's the Maxwell-Ampere law. And for a circular Amperian loop of radius r is less than r, we take B of 2 pi r. And this is equal to U naught epsilon naught d dt of E pi r squared. So this becomes B of 2 pi r is U naught epsilon naught pi r squared d e dt. B equals u naught epsilon naught r over 2 d dt. And since d dt, if we take the derivative there, that's going to be omega e naught cosine of omega t. So b rt, that's going to be u naught e naught omega e naught over 2 and times cosine of omega t, where r is less than r. Oh, and there's an r in the numerator too, lowercase r in the numerator there. And we say the direction is azimuthal. So our magnetic field is u naught epsilon naught omega e naught r over 2 cosine omega t phi hat. So part C, explain why Ampere's law without Maxwell's correction fails here for this displacement current here. So ordinary Ampere's law, if we write it out, says the following. Between capacitor plates, there is no conduction current crossing the gap, so ordinary Ampere's law would incorrectly predict no magnetic field. So Maxwell's displacement current term fixes this by accounting for the changing electric field. Okay, so that takes care of that one. And moving along now into 13. So 13, we have an electromagnetic wave. An electromagnetic wave in vacuum has electric field. E of zt equals the following. Part A, find the magnetic field. So the electromagnetic plane wave, we're given this function, E of zt. The wave what's going to do, it travels in positive z hat, and the magnetic field for a plane wave in a vacuum is B equals 1 over c, k hat crossed with the electric field, and here k hat is equal to z hat, so z hat cross x hat, that equals y hat. Therefore, we're going to wind up getting that magnetic field B of zt equals E naught over c cosine of kz minus omega t, that quantity, times y hat. Okay, for part B, find the relation between k and omega. The relation between k and omega for vacuum electromagnetic waves is just omega is equal to ck. Okay. And for part C, the time averaged pointing vector, the pointing vector is S equals 1 over u naught times E. So 1 over u naught E cross B, rather. So E cross B, when we do the math, we're going to get E naught cosine of kz minus omega t, x hat cross E naught over c cosine kz minus omega t y hat. Okay, so E cross B, E naught squared over c, cosine squared over kz minus wt, kz minus omega t. I often say wt just because it reads like a w. Z hat. So S equals E naught squared over u naught c, cosine squared quantity kz minus omega t times z hat. So the time average of cosine squared is 1/2. Thus, we wind up with the time averaged pointing vector being that we get E naught squared over 2 u naught over 2 u naught c z hat, or 1/2 E naught c E naught squared z hat. Okay, so that takes care of 13. So move to 14. Okay, so 14. We have a plane electromagnetic wave normally strikes a perfect conductor occupying z is greater than 0. The incident electric field is polarized in the x direction. Part A, write the incident and reflected electric fields in the region z is less than 0. Reflection from a perfect conductor. So for letter A, we could say the conductor occupies z is greater than 0. the wave is incident from z is less than 0, traveling in the positive z hat direction. So here, incident and reflected electric fields, we're going to let E sub I equal E sub naught cosine of kz minus omega t quantity, times that x hat. And the reflected wave travels in negative z hat. For a perfect conductor, the tangential electric field at z equals 0 must vanish. So the reflected electric field has opposite sign. So E sub r equals negative E naught cosine of now kz plus omega t times x hat. So when we go down here, okay, we have our total E naught cosine of kz minus omega t, x hat minus E naught cosine kz plus omega t times x hat. Okay, so that takes care of part A. Part B, find the corresponding magnetic fields. Okay, magnetic fields for the incident wave, so that B sub I equals E naught over C cosine of that kz minus omega t times that y hat. And for the reflected wave, the propagation direction is negative z hat. We need B sub r equals 1 over C k hat sub r. So crossed with E sub r. Since k hat sub r equals negative z hat, E sub r equals negative E naught cosine of quantity kz plus omega t times that x hat, and then B sub r is 1 over C times negative z hat crossed with negative E naught cosine of kz plus wt x hat. All that in brackets. And we wind up, we get negative z hat crossed with negative x hat. That equals positive z hat crossed with x hat. That's going to go out, and that's going to come out to y hat. So B sub r equals E naught over C cosine of quantity kz plus omega t times y hat. Therefore, we could say the total is here. B sub total is E naught over C, bracket, cosine quantity kz minus omega t plus cosine quantity kz plus omega t. I'm sorry, this was, did I say this is kz minus omega t, and this would be kz plus omega t. And that's going to be times, after we bracket that, y hat. Okay. And moving along to part C, the boundary condition. Show that the total electric field vanishes at the conducting surface. Okay, so at z equals 0, E sub I 0t is E naught cosine negative omega t, x hat. That's going to equal E naught cosine omega t x hat. E sub r of 0t, that's negative E naught cosine omega t times x hat. So our E subtotal of 0t, that equals 0. E subtotal z equals 0. T, that equals 0. So this satisfies the perfect conductor boundary condition for letter C. So that takes care of number 14. We can now move on to number 15. Number 15, and this is the last one in the practice exam for electrodynamics for today. So for 15, we have an electric dipole oscillating right here. We're given this rho of t equals rho naught cosine of omega t z hat. And in the radiation zone, okay, the electric field is proportional to E sub theta, proportional to omega squared rho naught over lowercase r sine theta cosine of kr minus omega t. So for part A, we want to explain why the radiation pattern depends on sine squared theta. Okay, so here, radiation from an oscillating electric dipole, we're given this function. So we're given this function, given P of t equals P naught cosine of omega t z hat in the radiation zone, E sub theta, that's proportional to omega squared P naught over R sine theta cosine of Kr minus omega t. So what we could say here is the radiation intensity is proportional to the square of the electric field amplitude, okay? And since E sub theta is proportional to sine sub theta, okay, our intensity here is proportional to sine squared theta, so our intensity here is proportional to sine squared theta. In what direction is the radiation strongest? Okay, so what we could say, so we dealt with the radiation pattern in part A. Part B, direction of the strongest radiation. Well, the radiation is strongest where sine squared theta equals 1. And this would occur at pi over 2. So at theta equals, that's a pi over 2. So the radiation is strongest in the plane perpendicular to the dipole axis, and that is at theta equals pi over 2. In what direction is it 0? Okay, so the direction of 0 radiation, well, the radiation is 0 where sine squared theta now equals 0. And this occurs at two places here where theta is 0 and pi. So there's no radiation along the dipole axis. 0 radiation occurs along, so 0 radiation occurs along the dipole axis. And then we have letter D, explain qualitatively why accelerated charges radiate. So here, part D, accelerated charges radiate. An oscillating dipole consists of charges whose positions change with time. Therefore, the charges accelerate. Accelerated charges produce time-varying electric and magnetic fields and detach and propagate outward as electromagnetic radiation. So that's all 1 through 15 in these two parts for this practice electrodynamics final exam. Hopefully it helps you, gives you some little bit more review in preparing for an exam in the course. And thank you for watching and have a great day.